Hi everyone, we are looking at part 3 of our 314 and 315 notes. So we have already looked at circles and roses. Today we are looking at limacons is what they're called, which is another type of polar graph. So we're going to use that same Desmos interactive. So if you could pull up the Bitly link in a separate tab, I'm also going to be using it. And I have another resource that I'm going to show you to try to hopefully make some connections between what we know about trigonometric graphs, our sinusoidal curves, with our polar graphs that we're looking at today. So for number 1, it says, open the folder and then press play on the B slider and watch what happens. And we're looking at part 3. So I'm going to show you real quick. So let's go to our Desmos. And if you just pulled it up, you want to make sure we're in the right part. So we're going to turn off all of our graphs. And I'm looking at part 3. So I'm going to open up that folder. And let's start with cosine. And it says press play on the B slider. So our B value is the number in front of cosine. So as we do that, we can observe what is happening. So I'm going to pause that. And now we're going to use this to graph the 4 graphs. I'm going to do the first 2, and then you're going to do the remaining 2. So the first one is R equals 2 plus 3 times cosine of B. So our 2 is our A value. So at the very top, our A value right now is 4. So we're going to change this down to 2. And our B value is 3, which is already at 3. So we have a graph that looks like this. We have an inner loop here. It's opening to the right. It goes out to 5. And so we're going to sketch this in our notes on that first polar graph. Now let's look at our second one. Our second polar equation is R equals 3 plus 3 times cosine of theta. So we already have 3 for the B, but we need to change our A value to 3 as well. So we're going to change that. And now we notice we don't have that inner loop anymore. It kind of looks like a lily pad is what I would probably describe it as. Some people say it looks like a heart. And now it's going out to 6, and it comes to a point at the pole. So you are going to use that same Desmos, and you're going to graph the remaining 2 of these 4. So we already have the first one that I kind of sketched in our notes, and then the second one. All right, so I want to try to make a connection between our polar graphs and our trigonometric graphs. So our polar graphs have R and theta in them, and we see them as R equals a number plus, there's a minus in this one, a number times cosine. We're only looking at cosine right now. If we were to rearrange these equations to look like trigonometric graphs, the 2 in this one would get moved to the end. The 3 would get moved to the end, so on and so forth. And now I have these equations where my input is my angle, my output would be like my y value. And we have our sine curves, and I only did one cycle, so from 0 to 2 pi. They are all cosine. This one has a reflection because of the negative, and I did sketch in the midline. So these are in your graphs. And what we're paying attention to is the part of this graph that could shed some light onto how the polar graph appears. So looking at the one on the far left, I notice that there's a little piece that goes underneath our x-axis. In the second graph, it just touches our x-axis. In the third one, it's kind of floating. It doesn't even touch the x-axis. And then for the last one, it goes underneath our x-axis again. So if we notice those characteristics, it helps us make a connection, because now when we compare our graphs, when it goes underneath our x-axis, we have that inner loop. And then the very last one, it went underneath our x-axis, we have that inner loop. When we have a gap and it does not touch our x-axis, it does not touch the pole. It has a dent, but it doesn't touch that middle part. And then if it barely grazes or just touches our x-axis, it's going to touch that point. It's not going to go through it like an inner loop, but just touch it. And so I want to show you another application that I have. So I'm going to slide back over. And this is a GeoGebra one. So I want to show you what happens. So this is one with an inner loop, and I'm going to push play. And we can see where our graphs correspond to each other. And the reason that the inner loop is created, I'm going to pause it, is because when we're at pi on the graph on the right, we have a negative output, but we know on a polar graph, if our angle is pi is to the left, but a negative r value pushes it into the other side. And that's what's creating that inner loop. Let's look at another one. I could do a sine curve. Same thing. If I have a negative output in my trigonometric graph, 3 pi over 2 is down here, but a negative r value pushes it to the opposite side. If we look at a cardioid, it's just a type of a limacon. It just touches our x-axis, and that is where it'll touch that pole and then get pushed back out. And then same thing here. So it just touches at pi over 2, but before that, we can see where it is on our polar graph. It goes back to the pole, back to the x-axis, and then back out again. And then the point that is the furthest distance from our x-axis is the point that is the furthest distance from the pole. So I'm hoping that that kind of makes a connection between what we have learned with trigonometric graphs, our sine and cosine curves, with what we're currently learning, our polar graphs. So let's go back to our notes. So we looked at 4 cosine graphs. Now I want you to take some time and you're going to graph the 3 sine curves, and I want you to make connections with the trigonometric graphs I have below. And then I just want to make sure that when you're on the Desmos, we're turning off cosine. So unclick that and then turn on your sine curve. All right, so you had time to do those 3, and this is what mine looks like. So I'm noticing the same things. If I have the negative part here, I have an inner loop, and so on and so forth. Something else to notice is there are other connections with these numbers, with sine and cosine, with positive and negatives, that tell us characteristics of our graph. So I want you to take a second and answer question number 4 and 5 on your own about what do you notice when A is less than B or when A is equal to B. And you can use the graphs that we've done. Remember, A is the number in front, but then B is connected to that sine or cosine. And then for number 5, what do you notice from any of the categories listed? What do you notice about the shape, the symmetry, the intercepts, the distance from the pole? And then come back to the notes and we'll fill in our quick notes. All right, so we're gonna put everything in our quick notes for limacon. So first, go ahead and make a divider. The stuff on the bottom will pertain to both sine and cosine, but the stuff on the top is specific to cosine or sine. So first thing is, it's called a limacon. That's the fancy name for it. So when we have cosine and we are adding on the inside, because we could be adding or subtracting, the longest part of our graph is on the right-hand side. And I have a little sketch there to kind of show that. And if we have a minus sign, then the longest side is on the left. And that makes sense to us because it's cosine, so it makes sense that it's widest along like our x-axis because it's cosine. So then for sine, if we have a plus, it is the longest on the top. And if we have a minus, it is longest on the bottom. And because it is sine, that makes sense because sine represents our y value, and we think of that vertical axis as like our y-axis in our Cartesian plane. So underneath, we're going to summarize hopefully what you kind of noticed in questions 4 and 5. So when we have the absolute value of A is less than the absolute value of B, we have an inner loop. And so we might have something like this. This one specifically would be a sine curve because it's opening like up and down. And our trigonometric graph would look something like this, where we have a piece that is underneath our x-axis that corresponds to that inner loop. Our second category is when our absolute value of A is greater than the absolute value of B. If this happens, there's no loop, and we would say there's like a dent. It kind of looks like a kidney bean, and so it doesn't touch the pole. It just kind of has a little indent there, and the connection with our trigonometric graph is that it does not touch our x-axis. So our polar graph is not going to touch the pole. And the last category is if the absolute value of A is equal to the absolute value of B. If this happens, there is a sharp point at that pole. And so we have something that looks like this. And this polar graph is actually a cosine polar graph, but I did still sketch like a sine curve. But just to show that it barely touches it here, so it's going to have that interpoint or that sharp point at the pole in our polar graph. So a couple things to notice, our intercepts are at the A value, and I'm going to pull up a picture to kind of show you that. Our maximum distance, or the maximum point away, is the absolute value of A plus the absolute value of B. And then our minimum distance, or our inside point, is the absolute value of A minus the absolute value of B. So to demonstrate that, I have this sketch here. Our equation is R equals 2 minus 3 times cosine of theta. So because it's cosine, I know it's going to open on the polar axis, either the left or the right. Because I'm subtracting, I know it's going to be on the left-hand side. And my graph kind of shows that it's opening to the left of the polar axis. My A value is 2, and if I look at my graph, my intercept here is at 2, and my intercept here is at 2, that second ring out. My B value is 3, so if I add 2 and 3, the absolute value of both, I get 5. That maximum distance out will hit that fifth ring, and then if I subtract those, I get 1, or negative 1, and my inner loop will hit at 1. And so that's what those 3 bullet points kind of mean. So that visual might help, hopefully. So we're going to look at one example together, and then you're going to try the remaining one. So example 1 says, in the polar coordinate system, the graph of a polar function is shown with a domain of all real values of theta for 0 to 2 pi. On this interval theta, the graph has no holes, passes through each point exactly 1 time, and as theta increases, the graph passed through the labeled points A, B, C, and D in that order. Which of the following intervals is the average rate of change of R with respect to theta greatest? So average rate of change, we're thinking slope, or the tangent line between 2 points. And we want it to be the greatest, which means we want it to be the most positive. So there's actually 2 ways we can do this. I'm going to show you both options. You can decide which option makes the most sense for you. So option number 1 is I am going to actually write an equation for this. We don't have the equation, but we can figure it out. So it's opening on the right-hand side. So I know it's going to be cosine, and because it's on the right, I'm going to have a plus sign between A and B. My intercepts here are at 4, so I know my A value is 4. And my maximum distance is out to the 7th ring, so I know A plus B equals 7. Well, if A is 4, that means B has to be 3 to get to 7. And then to double check, my minimum distance, this inside point, is 1. So when I subtract A and B, I should get 1. And so that tells me my equation is going to be 4 plus 3 times cosine of theta. Once I have my equation, I can sketch a general cosine curve that has that midline at 4. My amplitude is at 3. And so it'll go up to 7 here, it'll go down to 1 there. And then I kind of labeled where A, B, C, and D are located. A is at my angle 0, B is at my angle pi over 3, so I would say it's not quite to pi over 2. And then pi is where my point C is at. And then D is after 3 pi over 2, but not quite to 2 pi. So my sketch isn't super accurate, but we get the idea. So if we're thinking average rate of change, now I can kind of sketch my tangent line from A to C. So if I drew a straight line from point A to point C, it would be pretty negative. It would look something like this. If I sketch my tangent line from B to C, it would also be pretty negative. From B to D, it would be pretty horizontal. I know my sketch isn't accurate, but it'd be about 0. And then from C to D, it'd be positive. And so doing option 1, I would choose answer D because it's the only average rate of change that is a positive, which would make it the greatest. The second way to do this is to actually calculate the average rate of change. So we know for our average rate of change, we would subtract our outputs and divide them by the difference in our inputs. So what I did, now we're looking at the orange marker, I wrote all of the polar coordinates and I realized I wrote them backwards. So these are all flipped because our value is first. And so when I set this up, I can calculate my rate of change. And the only positive one is still from C to D. And so that tells me that my answer is D. So I want you to try example 2 and example 3. And then you can check your work with the answer key. And then you can work on your check your understanding problems.